have to sit further back.
That's a very small
Let's go live.
Do you know much about the conference?
small thing.
I mean, not a huge amount, to be honest.
Yeah. I think it's on me. Sounds fun. I just think it sounds really funny.
Yeah. No,
It's like a conference on middle-sized objects.
Yeah. It's
Small.
I feel like this is small, kind of restoring perhaps like Christian perspective
Yes.
from a philosophical and scientific perspective. I think it's great. It seems like we're getting great people.
Yeah, I think George Ellis is a very prominent cosmologist.
Yes,
Yeah,
very
very
promising. Are you coming to the
respected.
rest as well?
I'm not. I think these lectures, the next two are public lectures. Then I think it's a conference.
Yeah.
I haven't signed up or been invited to the conference. So these are public stuff. So yeah. How about you? Are you filming the whole thing?
I am,
Yeah. Sorry, should I let you concentrate on your task? I don't want to distract you if you're. I guess it's about to start.
That's right, but I'm heading back to the sound now. I'm multitasking a bit.
Well, anyway, good to see you.
You too. See you.
Nice surprise.
Indeed.
So they used to, before the pandemic, they used to be which was very nice because I thought it was going to be nice. I don't like it. If you don't get the same energy, I've done it this year. I mean, they're changing everything. So there's constant staffing. Everything is they used to be really nice. But then I did other things when I was there. There was quite a practical stuff. Historians and things and do some consulting. But those days are
Good afternoon, everyone, and thank you for coming. I am John Ritzler. I'm one of the researchers here at the Centre for Theology, Law and Culture, and it's a real pleasure to welcome you all here this afternoon to Pusey House. Two very brief points of housekeeping. Should you need the facilities at any point, there is a loo outside the chapel. You go out to the chapel, you turn right, then left, then down the stairs. You'll find the loos very easily. And the second point of housekeeping, during the interval, we'll have tea and coffee served in the common room at St Cross College, and I and a couple of volunteers will lead the way. So if you're unsure, it's in the floor, but we'll take you through there past the lodge. I'm now very pleased to hand you over for just a moment to Dr. William Simpson, who will say a few words introducing our lecturers today. Dr. Simpson.
Good afternoon, thank you all for coming. It's my privilege to introduce our speakers today. Professor George Ellis, a cosmologist based at the University of Cape Town, and Professor Robert Koons, a philosopher based at the University of Texas at Austin. George Ellis is widely regarded as a world-leading cosmologist. He co-authored the large-scale structure of space-time with Stephen Hawking and was awarded the Templeton Prize for his work at the intersection of science and theology. Robert Koons is noted for his contributions to philosophical logic, metaphysics, and philosophy of religion. In addition, he is a long-standing advocate of classical education, a fellow of the Civitas Institute at Austin, which is co-sponsoring our Colloquium. It's also my pleasure to introduce Professor Mark Harris, the recently appointed Andrews Interest Professor of Science and Religion at Oxford. Mark Harris is a theologian and condensed matter physicist, noted for his contributions to the interface of theology and science and his discoveries in the physics of magnetism. After the lectures and following a break for refreshments, Mark Harris will be chairing a discussion in which there will be an opportunity for the audience to ask some questions. The public lectures today are part of a program of talks and discussions this week bringing together scientists, philosophers, and theologians, in which we will be discussing the nature and reality of things that exist at the macroscopic or middle-sized scale. After all, the possibility of scientific inquiry seems to depend on the existence of middle-sized things, such as scientists and the instruments they depend upon to conduct their experiments. Yet there are significant questions about where middle-sized fits within a scientifically informed picture of reality. Are middle-sized things merely arrangements of microscopic things, or is there only one cosmic-sized thing of which there are many fragments? How do the mental properties of certain middle-sized things, like scientists engaged in experiments, fit within the world described by physics? Do some middle-sized things have their own cosmic capacities over and above the properties of their microphysical parts, which make a difference to how the physical world unfolds? These are questions which continue to exercise me as a philosopher with a background in physics, and there are some of the questions we'll be exploring together in our workshop at All Souls College tomorrow. George Ellis and Robert Koons are important voices in this discussion. Professor Ellis, who will be our first speaker today, has been a long-standing opponent of what he calls a purely bottom-up approach to causation in physics, which prioritizes microscopic reality and excludes the possibility of top-down causation from higher physical scales. Professor Koons has been at the forefront of a neo-Aristotelian revival in philosophy, which seeks to recover a more common-sense vision of reality in which the world contains natural objects of different physical scales that exercise their own causal capacities. I'm pleased to welcome them both this afternoon to discuss why middle-size matters.
Well, it's a great pleasure to be here. Thank you for the invitation, much appreciated. So I'm going to talk, as I say, about science of middle size restores purpose. Now, the universe can seem a purposeless and amoral place if one looks at it exclusively on very large or very small scales. There's a galaxy on the one side, a cluster of galaxies, and you're not seeing any purpose there. There's an atom and some molecules, and you're not seeing any purpose there. Now, to set the stage, I want to play, if I can actually just, a famous video, which is called Powers of 10. Many of you may have seen this. It's an old one, but it still is actually a very important one. And so we're into Powers of 10, and we can
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture is center of the pyramids, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie on their docks. The colorful bleachers are soldiers' field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first around the Atlantic Ocean, then the whole Great Lake, 10 to the 5th meters. The distance of orbiting satellite covers in 10 seconds. Long parades of clouds. The days In 1 second, the path crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun. Followed by the massive other planets, swinging wide in the big orbits. That orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one from the stars. Looking back from here, we know 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16 meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the white star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us to the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of the jungle. 10 to the 22nd power, a million light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way to our next goal, a proton in the nucleus of the carbon atom beneath the skin of the hand of the sleeping man at the picnic. A molecule like a long twisted ladder whose rungs of paired bases find ourselves right among those outer electrons. Now we come upon the two inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon the vast inner space. At last, the carbon nucleus. So massive and so small, this carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded to every molecule out to the farthest galaxy. As a single proton fills our sea, we reach the edge of present understanding. Are these some quarks of intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Well, I think you can see that's why that's a famous video made quite a long time ago. So now, the middle-sized scale of where biology occurs containing the existence of functioning agency. And the existence of such intermediate scales implies they are open systems, because if you're a very small part of the whole, then you've got a boundary, and so you're open. And that enables purpose meaning and ethics to be effective, and I will be talking about this. Many scientists specialize in either the very large, astronomers who look at the very large, like Carl Sagan, or the very small, like Stephen Weinberg, have emphatically emphasized there is no purpose in the universe. This includes some biologists who focus on the molecular scale alone. And paradoxically, they are ignoring their own lives when they make that statement. So it's a very strange kind of situation. So on the astronomical scales here, which we'll be looking at, the universe, the Milky Way, right down to the Earth, you can't see purpose on any of those. So that's the kind of structural walls and vacuums, the subtle kind of structure which galaxies form on a large scale. The nuclear scale again, which we're just looking at, crystals, atoms, atomic and nuclear quarks, you don't see purpose there either. Where you do see it is the biological scales, where meaning and purpose occurs from the cellular scale and above. And what you see there is the tissues, the body systems, the organism, populations, communities, and the ecosystems and the biosphere. And these are the scales. In terms of that big picture you're just looking at, this is right in the middle, basically where the whole thing started from. And if you look at the Earth from space, when you're seeing cities and the whole country, at that level you do see purpose because of the way that we cover the surface of the Earth with light. Now, a nice way to express this is what's called the cosmic Ouroboros. This is by Abrams and Primack and then by colleague Bernard Clark. And what you've got is the very small scales at the top on the left, and then go where they join up, and I'll explain why in a minute. And you go down the scale, so that's very small on the left, going down 10 to the minus 28, 10 to 10, 10 to the minus 10, the bosons. Then you see the atoms, you see the DNA molecule, you see cells, and then you see people, and then you see mountains, the earth, and the sun, the solar system, and so on up around the right. Now, the point about why this joins up is at the very biggest scales, quantum gravity was responsible for the origin of the universe. And so the nature of the universe as it is in the very largest scales is also due to the quantum gravity which underlies gravity at this very smallest. And so that's why this picture, the Ouroboros, is drawn in this way, so it closes up on itself with the different scales shown at the different sizes. Now, agency scales are those shown down there. If you look at that whole thing, that's the middle size scale. seeing all of those astronomical scales on the right, and you don't see it on all of the atomic and subatomic scales on the left. Now, the key point about the open system view is they have boundaries. And I've shown there a closed system there, and because they're middle-sized objects are middle-sized, they have an exterior and an interior and a closed boundary, separating them from the larger world. Forces in green impinge on them, and they exert forces. Matter in blue, energy in red, and information in yellow enter them and leave them. And because you've got a boundary, you've got stuff coming in and you've got stuff going out. Now, what that means is that 100% knowledge of their interior states is not sufficient to predict their future. The Pusey's demon, you've all heard of the Pusey's demon. If you know the states of all the particles, you can predict it forever. They cannot succeed their future states because stuff is coming in and stuff is going out. So this is an example of physical brain and the future. This is a woman who has just had a car accident. You can see the car in its ruined state on the right. And so she's on her phone and she's got a whole lot of new thoughts coming in which were not in her brain 10 minutes ago. What about insurance? What about a tow truck? How am I going to get home? So she's got new thoughts coming in which are due to the fact that new information has come into her brain after an accident. And what that means is if you have the position and momentum of every single particle in my brain, up at the top brain, for every atom in the brain, that's what the Pusey's demon wants to predict the future. That will not determine for you the future of the future of her brain because it doesn't take into account the new information that's coming into her brain because it's an open system. And this is the key point about an open system. The Pusey's demon cannot, in principle, predict the future. So, through evolutionary processes, evolution, talking in metaphorical terms, has discovered that living beings must develop agency to handle the situation. And so we have to be constructed so we anticipate the future and preemptively react to it by predicting what's going to happen and then taking action in advance where we can. So evolution has realized it's developed agency in order to enable us to survive relatively better. And the wonderful book about this is by Kevin Mitchell called How Evolution Gave Us Free Will. And I'm just going to illustrate one thing for you. We also predict what we ought to have seen. Our eyes are always predicting what we should be seeing and then telling us what our brain thinks we should be seeing. Now, here's the classic one. On the left, you can see the letter E, but there is no letter E on the left. There's just a couple of lines, but there is no letter E. On the right, you can see a triangle, but there is no triangle on the right. There are three circular bits with sections cut out, and your brain tells you, look, there's a triangle there, but there isn't any triangle. This is an example of the predictive processing that goes on in our brains. Now, this is one of my favorites. Can you read what that says? What it actually says is, what I have told you, but you read it, what if I told you? You actually cannot help yourself from reading it. What if I tell you? But that's not what is there. Your brain tells you to do that. Now, this is an amazing one. These are two circles. And in order to see that two circles, you've actually got to look very, very carefully. If I had a cursor, I could go around them. But in any case, your brain is telling you that it's an interconnected circle, but in fact it's two separate circles. Now I'm going to give you another one and see what you think of this. The first line is wrong, the second line is wrong, and the third line is wrong in your brain. Everything keeps catching you every single time, and this is the way predictive processing works in your brains. And so this is the kind of evolution has constructed us to handle this fact that we cannot in principle know what's happening, and it does it by enabling us to do predictive processing. Agency occurs at the human level on these medium scales, and we are actually familiar with it, but this is a lot of our physicist friends and others say we don't have agency, it's an illusion, but it isn't an illusion. Agency undoubtedly occurs relating to meaning and values, and examples are the construction of aircraft, computers, cathedrals, hospitals, teacups, and this channel. And those are all the result of human agency. They couldn't exist without human agency. They don't come to being by magic in some sense. They don't come to being by physics just saying to itself in some sense, I'm going to construct a cathedral. It comes in by human agency. And they each have a function related to our values and our purposes. So this is constructed by human agency. This is Jacqueline Dupre playing beautiful music. That instrument was constructed and she's learned to play it. This is agency, both of the people who made it and her playing it. Hospitals are an example of human agency. This is a hospital in my hometown, South Africa. And this is an example of what is inside of this whole thing is a result of human agency. There's very, very complicated medical equipment, all of that sort of stuff. But you can ask yourself, what actually is the purpose of this thing? Is the purpose of this thing to help people recover, or is it perhaps to make money? And that actually is one of the reasons to do this. This is a classic example. I love this picture of this little girl holding an umbrella to shield the cat from the rain. This is an agency without any ulterior motive. It's someone who's doing that just because they want to protect this little animal. I think that's a wonderful photograph. Now, how can agency occur given that physics is in some sense a highly deterministic system? And Philip Ball's book, How Life Works, talks about this in a lot of detail. And the point about this, there's a lot of molecular chaos at the lower levels. And in fact, all of the atoms in our cells are colliding with each other millions of times a second. And biology has discovered this and has worked out how to make. Now I'm going to try. Sorry, I want to just make that little thing play there. Yeah. Okay. This is a molecule called kinesin, and this is extracting energy from the chaos in the cell. It's a fantastic example of how biology extracts order for purposes. And so this thing walks along, carrying a load from one part of the cell to another. This is an example, if you like, of agency at the molecular level within a cell. And evolution has constructed that system in order that it would convey this from there to there, which is needed in order for the cell to function. In terms of the big picture we're looking at, this is a middle size, it's the lowest kind of scale at which function happens. And a paper which talks in detail about how this microscopic chaos enables purpose to arise is Dennis Noble and Raymond Noble. Can reasons and values influence action? How might intentional agency work physiologically? And that's the Journal for General Philosophy of Science, 52-277. And they have thought, he's in Oxford, he's a world-famous physiologist in Oxford, and has thought and written about this in a lot of great detail. Agency and causal completeness. How can agency arise in view of the causal completeness of fundamental physics, which many people talk about? And many people write about this. Physics tells it underlies everything and is obviously causally complete, and so agency cannot arise. This is the basic issue which many people talk about. Now, firstly, physics is not causally complete, and that's a key message of quantum physics. There's an impossibility of predicting the future in quantum physics. It's one of the absolutely fundamental features of quantum physics. So the people who talk about the causal completeness of physics, it isn't causally complete because of quantum physics. But much more important, it isn't causally complete because of upwards and downwards causation, which was mentioned in the introduction. There's a formal causation, material and final causation take place in addition to efficient causation at every level. I'm talking about this tomorrow in the workshop that my colleague here is going to be talking about a bit later today. And causal completeness only occurs when all the levels so causal completeness is only possible when you include all of those links between the different levels. Agency enables abstract causation to occur at human scales, and abstract causation is central to social life. And this is something I want to emphasize because, again, the reductionists never mentioned to you abstract causation. Abstract causation occurs in the rules of chess. The rules of chess govern the motion of chess pieces on the chessboard. And that is an abstract set of rules. Design for aircraft is an abstract and design for digital computer. And those designs are causally effective. Our thoughts change the world, and that is actually indisputable. Digital computers conclusively prove this, and there's a brilliant little book by Dasgupta called Computer Science, a very short introduction. And algorithms and data are abstract. They change the world via computers that are physical. And so what you have is you have a mixture of abstract causation and physical, and we can understand all the details of how that abstract causation works. And these are key aspects of our agency because we created the computers which entail abstract causation. And I want to quote from Dasgupta. Some computational artifacts are entirely abstract. They're not only precise symbol structures, they themselves are symbol structures, are devoid of any physicality. Though they may be made visible by physical media such as marks on paper or computer screens. So physical chemical laws do not apply. They neither occupy physical space nor do they consume physical time. And that's the nature of an algorithm. But that algorithm changes the world. They alter the world. Not only material causation takes place, it's a very, very important counter to people who claim that only physical things have to take place. And here's an example. Here's an automobile assembly line. It's driven by algorithms. It creates motor cars. Is meaning apparent at the molecular scale, the smaller scale? Now, there's a paradox here. Many molecular geneticists deny that function or purpose occurs in biology. Now, it's not very apparent in the coding of genes, the ACGCT sequences. If you look at that sequence, you can't actually see much purpose there. And a key point is something I would emphasize again tomorrow, multiple realizability. When you have a higher level function, it chains down via evolution to the lower levels. It can be realized in many, many different ways at the lower level. But agency is visible in proteins, and macromolecular structures are driven in a downward way. You need to take physiology and ecology into account to explain. And here's an example. These are ion channels. A voltage-controlled ion channel. There's a view from the left on the left, a view from the side on the left, and a view from the top on the right. It's got a structure of 4 panels, which you can see in the top view, and the ion channel is open on the right, and on the left you can see the two, these are the ones at the top, and they open and close depending on the voltage across the ion channel. So on the left is the voltage-gated ion channel closed from the side, on the right is the voltage-gated ion channel open with the little ion passing through. Now, these have come to be what they were because of evolutionary processes. Every single one of your brains got billions of these little things allowing ions to go in now, which enable action potentials to go in your brains and enable functions to take place. And so such molecules came into existence by evolutionary selection. They underlie how the brain functions and enables us to thrive. And so you can see function and purpose at that level because those are there to enable the brain to function. That's the lowest level at which you can see function in molecular terms. I'm finally going to talk about the highest level, in the Ouroboros. Can you see purpose at the topmost scales? And there are 2 key issues that arise when we look at this confluence between the quantum gravity and the smaller scale and cosmology at the larger scale and how they meet each other. And the first one is the so-called anthropic issue. The universe has a special nature that allows life and purpose to exist. And this need not have been the case. If physics on the left had been very, very different, life wouldn't have been possible because perhaps protons and atoms couldn't have existed. And there are a set of constants of nature, such as the ratio of the masses of the proton and the electron. It has to lie in a very constrained rate, or there wouldn't be any all enabling life to exist. In cosmology, on the right, it has a very strong set of constraints on what can happen in order that life can exist. For instance, the so-called cosmological constant is pushing the universe apart at a very fast rate at the moment. If it was very much bigger, there would be no structure in the universe, and so there wouldn't be any stars, planets, or galaxies, and life would exist. So none of the evolutionary processes leading to life as we know it could have occurred if either the physics was very different or the cosmological context was different. And this is called the anthropic issue. Our universe is in this sense a fine-tuned universe. The possibility of agency and purpose is embedded at the very largest and very small scales through this fine-tuning on the small and the large scale. So you might say to yourself, actually, I can see the pre-image of life in both the small and the large because of this. So why is the universe apparently fine-tuned? And many of my colleagues on the science side say it's because we live in a multiverse. And I'm not going to go into the details, we can talk about it if you want to. But the fine-tuning in the end is, in my view, a metaphysical question. It's beyond the scope of science to answer. And the final question, which is a fundamental one in all of this, is the universe itself deterministic? So you can say, what you've told me is all very well, but in the end, what has happened is determined by the initial conditions of the universe, and there was no option. The outcome had to be what it be. And so all of this apparent agency we're talking about is actually nothing but, the famous phrase, nothing but an inevitable outcome of the initial date of the universe together with deterministic physics. So are free will and agency illusions because physics alone determines everything? Now to make this specific, what I want to ask you is the following question. Can all the words in Shakespeare's sonnets be uniquely implied by initial data in the very early universe? Now to give this its proper context, we must look at our current understanding of the history of the universe, and going from left to right, you've got the Big Bang on the left, you've got an inflationary expansion, you've got dark ages, you've got the formation of galaxies, stars, and the present age on the far right. And quantum fluctuations lead to the existence of structure, and time goes to the right. Now, that's the context. And the question you have to ask yourself is it possible there that this physical process, which I could describe to you much greater, could that physical process result in some sense of the words of Shakespeare's sonnets being encoded? And that's absolutely impossible. The result of those quantum processes is random Gaussian perturbations, later modified by astrophysical processes that even later produce stars and galaxies. And this is a wonderful picture by the WMAP satellite showing these fluctuations on a very early universe. And there's nothing remotely resembling a coded version of Shakespeare's sonnets in the state where astrophysical processes cannot possibly produce that result. And furthermore, even if it was coded, that biological developmental processes couldn't possibly stick that information into Shakespeare's brain, and I could discuss that at length. There's no way that could happen. And so the idea that the universe is deterministic and apparent agency is due to physics alone is simply wrong. There is no way that could actually work out. The cosmic context of ordinary life, the expansion of the universe produced galaxies, stars, and planets. Chemical and biological processes on suitable planets produce life. That sometimes involved a state of conscious awareness capable of high-level thought and purposeful action, such as writing meaningful sonnets that rhyme. This is allowed by the underlying physics together with the initial data, but it is not uniquely determined by it. It's emergence which enables us to come. And that emergent process means what happens in the universe is not uniquely determined by the initial state of the universe. Emergence enables meeting and ethical stances to take place at human scales, enabled by the four forms of Aristotelian causation. Physicists who take into account only the physics and cosmological data proclaim that there is no meaning in the universe. But this is a selection effect resulting from the scope of the data they choose to take into account. It leads to the paradox of thinking it is meaningful to make statements that the universe is meaningless, and obviously that's a paradox. Why and how does all this purpose exist? Physical, biological, and mental functioning together allow it to emerge at human scales in open systems. And my final slide, this beautiful picture exists because of the it depicts much more than just material existence. It's got a kind of ethereal nature to it. The specific nature of the universe made its existence possible, but not inevitable. It occurs at a human scale. It's not visible for what it is, at very much larger or very much smaller scales.
Well, I'll just bring up Professor Koons' PowerPoint. I'll point out that there are some free seats at the front. There's 9 or 10 free seats if any of you are struggling to see the screen from the back.
I want to thank you all for coming. It's a real honor to be here in Oxford, especially to be paired with someone whose work I admire so much and has such an influence on me, Ellis. So thanks so much for that. Thank you so much. So I have a vivid memory of a seminar in 1983, I think it was, led by Robert Bouverie Pusey from UCLA, who sadly died this last month. He told us that he found the Aristotelianism of the scholastic period extremely attractive, but as a basis for human value and human agency. But sadly, the scientific revolution happened and is now obsolete. So that question's been bouncing on my head for 40 years, I guess, right? Is it scientifically obsolete? Is there a possibility of reviving Aristotle in this respect? Now, Aristotelianism has undergone great revival. Great revival in the intervening 40 years since that seminar, with Aristotelian approaches to ethics, both in terms of virtue ethics and theories of natural goodness, and also the scholarly defenses of Aristotle's approach to science, Charles and others. And later there's been a revival of Aristotelianism within metaphysics as well. But all this revival would seem to me to be ultimately ill-fated, unless we can overcome that challenge that Bob Adams mentioned in 83, because can we show that this Aristotelian approach is still viable? So my talk's in 4 parts. I'm going to start out with Aristotle's vision of nature, talking briefly about the non-rejection of that. The bulk of the talk will be in the 3rd part, where I argue the recovery of Aristotle. So we'll take the 4 points of convergence, an introduction to 4 points of convergence. And then, if time permits, I'll say a little bit about organisms in the soul and how I think this might relate to the interests of people working in philosophy, biology, and philosophy of mind as well. So, let's go on to Aristotle's vision of nature. Philosophy has been from the very beginning prejudiced, I think, against the middle-sized world. Priorities have been given by people like Democritus, who are very small, or by Maimonides, who are extremely large. But only Aristotle really provides us with a theory of the world, philosophy of nature, that privileges the middle-sized sort of object. So it's worth looking at. In Aristotle's philosophy of nature, the relationship between wholes and parts is complex and variable. In some cases, the parts are prior to the whole. The whole is a mere heap of constituents. In other cases, however, the whole is prior to its parts, in the sense that the parts derive their reality and their agency from their participation in the life of the whole. This is supposed to happen most especially in organisms, including human beings. But there's an even more fundamental feature of Aristotle's philosophy than this introduction of both actuality and potentiality as distinct modes of being or reality. A complete description of reality, according to Aristotle, is taken into account not only how things actually are, what's actually happening, but also must include descriptions of what actions could take place, and what changes and processes could be undergone. Consequently, Aristotle has explained change in terms of the interaction of causal powers, the intrinsic potentialities of things. The theory of causal powers, I think, leads quite logically to Aristotle's 4 causes, that of efficient, final, formal, and material process. Aristotle's way of accounting for change, namely that change is the result of the exercise of causal powers, rooted in the natures or essences of the agent and patient involved, is called efficient causation. This Aristotelian model of efficient causation does not seek to describe the changes as conforming to some abstract law of nature or motion, but rather attempts to understand the changes as the expressions of the powers, potentialities of the objects involved in it. Aristotle's efficient causation gives us irreversible changes in processes at a very fundamental level, since every causal power is a causal power to move from one state to another state. Aristotle is thus able to define time as the measure of change, which gives time a fundamental error, intrinsic error. Final causation, or teleology, also follows logically from this theory of causal potentiality. Every causal power involves what George Molnar and David Armstrong described as natural or physical intentionality. A causal power is defined in terms of its possible manifestations, whether those powers are ever actually exercised. And this is exactly the indicator of intentionality. Intentionality can relate us to things that don't actually exist. So Aristotle and Aristotelians like Thomas Aquinas mean really nothing more than this by final causation, as in his book, Theology. So if something has a causal power, rooted in its essence to act in a certain predictable way, that is final causation. So it doesn't require any sort of description of a yearning or desire to things, nor even to some prior conception of good that's being pursued. Now these causal powers are not distributed randomly in nature, right? Instead, we find material things divided into natural kinds or species. The nature and essence that's shared by things in the natural kind corresponds to Aristotle's third kind of cause, formal causation. Now, in addition, Aristotle talks about the intrinsic states of things, like temperature or momentum, as accidents. And accidents also stand in a formal relationship, formal causal relationship with substances that have those accidents. Formal causes, therefore, confer causal powers on some subject. These subjects then constitute Aristotle's fourth cause, the material causation. The relationship between formal and material causation in Aristotle repeats itself in a hierarchical fashion. This is where we get back to those size objects. So at the bottom are the entities with little or no intrinsic nature at all, something like God's energy, perhaps. At the top of the hierarchy are fully formed entities called substances, in Greek. In between are material things characterized by more or less proximate kinds of matter, in Aristotle's picture. So in the case of an inorganic substance, which is typically homogeneous in nature, we could go from a very bottom level, let's say God's energy with relatively little intrinsic nature. Then we could talk about a massive fermionic matter, so we've got a little bit more form added to that energy, then up to a body composed of oxygen and hydrogen atoms, atomic forms are being added, and then finally a body of water, the molecular structure as well. Now in the case of an organism, a body of water might be a part of a structured organ. Organisms have this further structure of heterogeneous organization. And so we can continue the hierarchy, right, by the fifth level talking about the body being composed of various sorts of chemical substances like aqueous solutions, fats, and so on. Then a body composed of various cells, and that's cell structures. And then a body composed of avian organs, and then finally the sparrow at the very top of this structure. So we have a hierarchical kind of organization of formal causation in Aristotle's picture. So material explanation in general is bottom up. To use this analogy again, we explain the characteristics of a whole in terms of the characteristics of its parts and their relationships to each other. We explain the flammability of a book in terms of the flammability of the pages of the book. We explain the shape of one of the great pyramids in terms of the spatial relations among the constituent blocks of stone and so on. Formal causation, on the other hand, is top down. To get the formal cause of a thing is to elucidate its essence, what it is to be of a thing of its kind. And the essence of a composite thing, composite substance, constrains the natures and mutual relations of its parts. The essence of each part depends on the essence of the whole in which it participates. For example, to be a heart is to be an organ that plays a certain role in an organism's circulatory system. To be a gene is to be part of a DNA molecule that codes for a certain production of a certain enzyme, and so on. So that's a very quick introduction to Aristotle's picture. Now, a modern objection to Aristotle. In the modern, so we philosophers call modern something from the 17th century to roughly the late 19th century. The modern image of nature, dominant from the time of Galileo and Bacon until the quantum revolution, contrasts radically with Aristotle. First, on the modern view, all fundamental material entities are simple and microscopic in scale. Thus, every composite thing is a mere heap by Aristotle's standards. Modern science also seemed to have no need for causal powers and potentialities. They were dismissed as occult qualities. It seemed to be sufficient to describe, by means of mathematical equations, what is actually happening in the universe. In the place of causal powers, changed to explain in terms of conformity to abstract mathematical laws of nature. There seemed to be no need for efficient and final causation, then, as Aristotle conceived them. The French biologist Edward Bouverie clearly expressed this kind of attitude by saying, the final cause does not intervene as an actual efficacious law of nature. So notice that Bernard cannot conceive of any causation except that expressed by the law.
The enduring logical consequence, vital properties, biological properties, are in reality only physical chemical properties of organized matter. Now, with the loss of causal powers, modern science has demoted irreversibility in time from a fundamental fact about change in the world to a byproduct of contingent, perhaps even local and temporary conditions. The fundamental laws of classical physics were all-time reversible. Now, this reconceiving of efficient causation rendered formal and material causation also superfluous. If there are no causal powers, there's no need to posit forms or accidents as the ground for those powers. Without formal causation, we lose the hierarchy of distinct kinds of proximate matter. So Aristotelian material causation also must have solved the causes go. And instead we think of matter as a relatively uniform, homogeneous stuff, moving eternally according to mathematical equations of motion. So in the so-called period of classical physics and chemistry from Galileo to Rutherford, the appearances seem to be against isomorphism, against Aristotle. If the ambitions of physicalists had been realized, if all natural phenomena had been accounted for in terms of the locomotion of uniform matter, then the framework of isomorphism would have no purchase. But we have to distinguish it between aspiration and achievement. The physicalists aspired to make the substantial forms superfluous, but they did not succeed in doing so. In fact, natural science never achieved complete reduction of chemical and biological kinds to facts about the movement relations of physical particles. Chemists and biologists continued right through the modern period to appeal to the enduring natures of compounds and organisms in their scientific explanation of the phenomenon. But this brings me to my central point of the lecture, which is the claim that quantum physics and chemistry in particular have vindicated Aristotle in some sense. That is, at the very least, the natural world as revealed by quantum theory coheres very amicably with an Aristotelian philosophy of nature, kind of expect early on, giving to the hieromorphous ample scope for the philosophical illumination of the natural processes. So this section I'm going to run through 5 points quickly if I'm able to. And first of all, a preliminary point about the incompleteness of the physical world before the quantum revolution. But then 4 points where I think that there's a convergence between quantum theory and Aristotle. So this is going to be the question about actual potentiality for causes that I talked about, the irreversibility of some natural processes, and then the irreducibility of chemistry and dynamics, and then finally the measurement problem, hopefully I get to all that. So the completeness of the physical world. Before I get to the details, I want to talk about that. So one important aspect of the 17th and 18th century was this emphasis on what Aristotelian describes as a kind of material causation. That is, explaining things through hypothetical necessity. If large systems were to behave as they're observed to behave, they must be composed of parts with intrinsic natures and mutual arrangements in space that are capable of sustaining that observed behavior. So from an Aristotelian point of view, this approach is perfectly legitimate. It's illuminating, obviously, to be told that water is composed of H2O molecules, and that DNA, that cells containing double unison of DNA. Where from an Aristotelian point of view, this microphysicalism goes wrong is insisting that the macroscopic phenomena can be exhaustively explained in terms of microphysical facts. Very much what George was talking about earlier. This microphysicalism, which is common both to the ancient materials like Democritus and Nutritius, and modern physicalists like Quine and David Lewis, has always, I think, stood in some tension, at least, with our common sense understanding ourselves as agents, as rational agents. For example, in Plato puts into Socrates' mouth an argument against the microphysicalism of his day. It seemed to me it was very much as if when, in trying to give out causes of a particular thing I do, which should say that I'm sitting here now because my body is composed of bones and sinews, and the bones are hard, have joints, and divide them, and the sinews can contract and relax, and the flesh and skin which contracts them are laid upon bones, and so on. And should fail to mention the real causes, which are the Athenians decided it was best to get identity. And therefore I decided it was best for me to sit here. It was right for me to stay, and then go with an empty the end go. So microphysicalism, at least prima facie, creates a problem as where we fit rational agency into the picture. How do we exist as rational beings in a microphysical sort of world? Now, long before the quantum revolution, an anti-realism about what Wilfred Sellers called the manifest image of man, in favor of what we call the scientific image. I think it was the microphysical image. This already was threatening, I think, to undermine the scientific enterprise itself. Since our observations and experiments presuppose the existence of observations and experiments, right? microphysical image and the experimental image of the world that the experimental science works with. How can we bridge the gap between the two? If we cannot, our microphysical theories are left dangling without experimental support. So there are always some grounds for doubt or suspicion about the microphysical's ambition. But the success for so long was an outlaw classical physics suggested this claim must be true, whatever its philosophical conundrum. This changed the thing dramatically with quantum evolution. That's going to be the point of this section. The solution is perhaps not making microphysicalism untenable, I won't say that, but it's clearly put it on the defensive. It's opened up a live possibility of resurrecting substantial forms of macroscopic scales, including the scale of human beings and other entities. So it was Bouverie Heisenberg who first recognized the connection between quantum theory and Aristotle. As he wrote in Physics and Philosophy of Physics in 1958, that quantum theorists simply rediscovered Aristotle's notion of potentiality, Heisenberg got it exactly right, I think. Prior to the quantum revolution, scientists treated the domain of potentiality, the possibility, as merely a useful fiction, a realm of mathematically conceivable possibilities or thought experiments. The real world, in contrast, is supposed to consist entirely of the actual, an infinite sequence of actual positions and momentum, linked together by deterministic natural laws. In those sciences that seem prima facie to depend on the objective probability of chance, like thermodynamics or natural selection, the appeal to chance was believed to be reducible to our ignorance of the exact positions and momentum. So no real need for potentiality in the description of the world itself. Quantum theory has changed all that. In quantum theory, you cannot explain what actually happens without appealing to what was merely potential in nature. For example, in Feynman's sum over histories or path integral technique, George mentioned that too, one's empirical predictions must take into account the sum total of the potential paths of the particle, including those which are not actually taken, if any. So from potentiality to the four causes, efficient causes explain the transition from potentiality to actuality through the exercise of some causal powers, and potentialities give us final causation, teleology. Now, it was Leibniz who first recognized that in physics in particular we have least action principles, and Leibniz recognized that these were explicitly teleological in character. Max Planck in 1930 emphasized exactly the same point. I'm going to quote this to some extent, most of the quote here. In fact, the least action principle introduces a completely new idea of the concept of causality. The causa efficiens, which operates from the present and makes future situations appear determined by earlier ones, is joined by the causa finalis, for which conversely the future, namely definite goal, serves as the premise from which can be deduced the developments and processes which lead to the goal. So this kind of physical causality possesses an explicitly teleological character, according to Planck. So when we use least action principle, we explain what's happening in terms of what has happened and could happen throughout a whole course of change. In the modern era, philosophers of nature generally consider least action or variational explanations to be relatively superficial in nature, as merely the exploitation of an odd coincidence among two mathematical formalisms. It was assumed that causation in terms of the parallelogram of forces, pushings and pullings, modeled by differential equations, provided a real fundamental explanation of change. But things look quite different after the quantum revolution. Although we continue to use differential equations in the form of Schrodinger's equations, they no longer have a natural physical explanation in terms of the pushing and pulling forces. Moreover, the scientific revolution of the 20th century preserved the classical least action principles intact in a way that no explanation in terms of Newton's forces was survived. So we now have good reason to think that it was an explanation in terms of Newton's forces that was relatively superficial. The real deep explanation has always been a teleological one, which lives on in Feynman's sum over histories work. Andrew Steen recently has expressed a similar view. I'm going to quote this in some detail. The notion of gradual evolution through time, described by a differential equation, while it can be presently used with sufficient interpretive statements accompanying it, is not the natural language in which it described the real world. To illustrate the point, consider classical mechanics. This could be mathematically treated both by a differential equation describing gradual evolution through time, and also by a path integral or least action method. The prediction is the same in the classical case, and in the classical case there's no difficulty in making a close comparison between the two. suggested elementary equations. However, in the quantum case, I'll argue, the path-predictable method gives a better physical picture than the time-dependent differential equation. And Steen's not alone in this. A lot of physicists will agree on that. Okay, the irreversibility of some natural processes. At the time of Schrödinger, at the level of Schrödinger's dynamics in metaphysics, there's no true irreversibility or direction of time. There's therefore no microphysical process that is intrinsically directed toward the future. However, if we accept thermodynamics as a fundamental science applying to substances, then the second law of thermodynamics gives us a fundamental and intrinsic direction to time. And this gives us a natural teleology in the inorganic world, in addition to its action principles, as systems naturally seek their equilibrium state. Now, a number of prominent physicists have argued since the quantum revolution that the correct interpretation of quantum mechanics restores true irreversibility in time to nature. I can mention Bernard Spinera, Rubio, Hans Primus, and all those defend any kind of form of objective collapse theories like G-Garden and Penrose. Again, Andrew Steen expresses that they're also a member of this group. The second law of thermodynamics, the concept of entropy are commonly regarded as useful devices rather than insights into the basic fabric of the world. However, according to Steen's quantum event postulate, microscopic evolution is a subtle mixture of reversible and irreversible components. Therefore, Steen argues entropy is a basic ingredient in any fundamental physical theory, not merely a populational device. So this is, again, peculiar to Steen's theory, but there's many physicists who work in this area who agree with Steen about that. Fourthly, or the third point of convergence, the irreducibility of chemistry and thermodynamics. This is a big subject. I don't have time to go into much detail, so I'll just give you the 30,000-foot version of it if I can. So in quantum mechanics from the 1930s and 40s, typically, at least, the system was modeled by means of a Hilbert space and a unit vector within that space representing the whole universe. Each unit vector corresponded to a property of an observable, and the quantum observables were subject to Heisenberg uncertainty and were typically in a state of superposition. You have a unique arbitrary measure. Now, the Stone by Neumann theorem in 1931 demonstrates that any two complete representations in a separable system, and any system that has finite many degrees of freedom, and indeed any system that has finite many subsystems will become separable. Any separable Hilbert system are unitarily equivalent, and the unitary equivalence is used to represent macroscopic states. So that means that they're all in the same macroscopic state. So separable systems are useless for chemistry and thermodynamics. You don't get the disjoint superselection sectors that you need to represent distinct temperatures, distinct phases of matter, and so on. And separable systems, as I'll explain in a minute, do not allow for spontaneous symmetry breaking or phase transitions. So any pair of finite parameter systems are unitarily equivalent. This means that any two systems with the same total energy and the same number of particles are going to be macroscopically indistinguishable. This means in turn there can be no difference in the macroscopic scale in chemical composition, phase of matter, or entropy. And thus would seem to make chemistry and thermodynamics impossible. So what do scientists do? What they do is they take their models to the continuum of thermodynamic limit. Okay? Create a non-separable model. In non-separable quantum systems, the Stone by Neumann theorem fails. Such models always have infinite many degrees of freedom and subsystems, and we get inequivalent representations, unitarily equivalent representations. So Hilbert spaces that can represent macroscopically distinct situations, like distinct phases and temperatures and so on. To get there, let's say we have to go to the thermodynamic continuum limit. So in effect, we treat the system as if it contained an infinite number of infinitesimally small molecules or other particles. The individual atoms and molecules end up being, I would say, merely virtual parts of the system. So it's only if this limit, that the models have enough internal structure to distinguish the different chemical compounds in different phases of matter. And only that limit can we give rigorous definitions of central notions like temperature, entropy, or chemical potential. So the use of non-separable infinite models in quantum statistical mechanics realizes a higher order model of explanation. The fact that we must take these models to an unrealistic limit with an infinite number of infinitesimal particles represents the role of formal causation. Material causation, which would involve actual number of particles, trying to work from bottom up, cannot fully capture the system's thermodynamic properties. So substantial form is responsible for these thermodynamic properties. It's also responsible for the chemical composition of substances. The geometrical structure of molecules cannot be captured by pure or finitistic quantum mechanics without taking the models to this continuum or thermodynamic limit. It's true that once we have the geometrical structure of the molecule, as revealed by experiments, we can then use in pure quantum theory to explain the stability of that structure. That's just what high-quantum would expect. Pure quantum theory provides the material explanation. It explains how chemical forms are stable. However, quantum theory cannot give us the explanation of chemical structure itself. So Robin Henry agrees with this. He says the quantum theoretic explanations of chemistry are essentially parasitic on the classical accounts they're supposed to supersede, because they certainly make no sense against the background of rigorous quantum mechanics. They say the semi-classical nature of the molecule is presupposed. And Robert Bishop says something very similar in 2005. So we might object that the contextual emergence, which is also very close to George Ellis' picture in the Barbara Gospels, violates one of the core principles of atomistic physicalism, microphysicalism. Identified, for example, by Robert Van Boele, on microphysicalist picture, the only law-like regularities needed for the determination of macro features are those that govern the interactions of those micro features in all contexts, systematic or otherwise. The example of molecular structure does not respect such a molecular principle of quantum mechanics. So molecular structure is a top-down formal kind of phenomenon from Bishop as well. Spontaneous symmetry breaking in a pure quantum theory that's the absence of the thermodynamic limit, the continuum limit, is such that cannot explain spontaneous symmetry breaking, unlike classical mechanics. Such breaking of symmetries occurs only at this so-called unrealistic limit. Therefore, all asymmetric chemical structures, like the left-handedness of organic amino acids, must be imposed from above by Aristotelian form, not in a bottom sort of way. Chang Liu in 1999 says phase transitions are well understood phenomena in thermodynamics, but it turns out that they are mathematically impossible in finite statistical mechanics systems, in quantum mechanics. Hence, phase transitions are truly emergent properties. They appear again at the thermodynamic limit. Thus, quantum thermodynamics and chemistry provides us examples in which the macroscopic features of the system do not even supervene on, and therefore cannot be exhaustively explained by the microphysical features. Okay, hopefully I have time to get through the next section of the measurement problem. This is a bit complicated, if we take the formalism of quantum dynamics at face value, quantum mechanics explicitly points to the incompleteness of the microphysical. This is because the formalism defines the microphysical exclusively in terms of probabilities. But probabilities of what? The original official answer is probabilities of measurement results. But what is a measurement result? So from Niels Bohr, a measurement result is an event in the classical world. Bohr held that reality can be divided into two disjoint realms, the quantum world and the classical world. For Bohr, all we can know about the quantum realm is that it determines certain probabilities for events in the classical world. Now, many physicists were unhappy with Bohr's solution, since it seemed to overlook the fact that the classical world is composed of quantum things, quantum particles. So how can the two domains be kept separate? So here's a sort of statement of the measurement paradox of quantum theory. Quantum dynamics seems to describe only changes in probabilities of measurement results. 1. 2. These probabilities are probabilities of measurement events. 3. Measurement events are entirely opposed to quantum events, so therefore must consist of change in quantum particles. 4. Let's assume that quantum dynamics is the only correct version of dynamics of any process composed entirely of quantum events. So, 5. The measurement events must consist of nothing but changes in probabilities. But this results in an absurdity of regress. Probabilities being everything to anything actual. So I'm reason I'm trying to skip over the Schrödinger cat stuff. No, that. I got 5 minutes. Okay. Well, maybe I'll talk about them real briefly today. So in the famous experiment of Schrödinger's cat, this is sort of illustrates the first step of the regress, right? As I'm sure you know. If we 50% probability alive, 50% probability dead. Of course, this is just, the cat here is just a stand-in for the human observer, right? So in a similar way, you end up with a human observer who's got 50% probability of observing spin up, 50% probability of spin down. And if you then say, well, the only way that means that some observer will see the observer in this state 50% of the time, then you get the infinite regress, right? That observer is also a quantum system. Then in fact, that observer will also be in those states. And now again, we probably have some further observer, right? Another observer, and so on, so you get this infinite chain. So that points to the need there's some sort of a way of resolving this paradox, right? Here we can break this down into a couple of possibilities. Basically, we deny, I think, either 1, 3, or 4. And Bohr denies 3, because he tries to divide the world into a classical world and a quantum world, and the classical world is not going to quantum stuff in Bohr. Neumann and Wigner also deny 3, I think, because for them, measuring events are actually mental events. The mental events are not opposed to quantum things, right? So that's another way to deny 3. Much more popular in recent times would be to deny 1. To say that quantum dynamics is not just about probabilities, in fact. Right? So on the Bohmian mechanics, and also other hidden variable mechanics in the area of modal interpretations of quantum mechanics, that you would take the quantum mechanics also be a pilot wave, a guiding wave that's actually moving particles around, and not just giving those probabilities ultimately. And similarly, I think we could put the Everettian many worlds interpretation into this camp of denying 1 as well. So you might say, we're not really talking about probabilities anymore, we're talking about some kind of weight in these different branches, all of which are equally real. Right? But there's also the possibility of denying instead 4. Right? That is saying that the quantum dynamics is not the correct description, the only correct description of what happens in things that compose of quantum particles. Right? So obviously GRW, Penrose, other sorts of objective clocks used to do this. They'll supplement the dynamics with something new. But in those cases, they're rejecting, talk about that. They're doing so at a microphysical level. That is, they're adding a new mechanism in terms of the number of particles that are entangled in a certain way, or some other kind of phenomenon that's microphysical in nature. Hylomorphous, Aristotelians, pluralists more generally, are going to reject 4 because they argue that large-scale objects like us are also subject to fundamental non-quantum laws that apply to the level of chemistry, thermodynamics, biology, and so on. Right? And so that's another option, another way to get around the paradox. This is a quote from Aristotle and Ellis. It illustrates this kind of view. So even in the context of quantum systems can be described quantum mechanically, at least for some degrees of freedom, not to certain lengths and timescales. The wider environment is a classical environment. Quantum mechanical calculations depend on classical concepts of classical environments for those degrees of freedom that are not explicitly modeled. So there's no eliminating the non-quantum dimension here, the non-quantum dynamics that operate in the world. Okay, good. So I think a chance to talk about organisms, so let me listen real quickly about this. I think George actually mentioned this already, that on this sort of Aristotelian view, real difference making is possible at the chemical, biological, and ultimately psychological level, because of the stochastic and deterministic nature of the underlying microphysical dynamics. And I want to say something in closing for those who are interested in looking at this problem from a more dualistic picture. There's a couple of audiences do, right? So I'm right there in the third row. So I'll say something about it. Here's a reason why you folks should also be interested in the project that I'm working on. Why some kind of polymorphic approach here could actually be a benefit. And I think it would come with 2 problems in people's space. One is the pairing problem, right? So we want human souls to be attached somehow to human bodies, right? But we can't identify human bodies with arrangements in microphysical particles, because neither the arrangements nor the particles are persisting over time. So what is it that persists over time? It's a biological entity, right? And so we have to take biological entities seriously, and the polymorphic approach does that. Finally, there's the interaction problem. How does the soul affect the body? If you try to combine, let's say, Democritean microphysicalism with dualism, then you've got to attribute some pretty fancy powers to the soul, right? It's going to have to be able to choreograph the movements of trillions of tiny particles in order to see, what do I need to do to get the candidates? What do I need to do? How do I need to respond to the particles that move around the brain? I think the Aristotelian picture, especially with the idea that there's this hierarchy of levels from the top to the bottom, it helps us with kind of vision of labor. Right? So the soul can be involved in affecting the biological features of certain organs, which in turn affects turn helps determine the quantum level. So there's a nice sort of cascade here of influences that makes the interaction probably more intelligible, I think. Okay, and I was going to, if I did have time, I was going to conclude a couple quotes from Aristotelian and Nancy Cartwright, delineating this sort of approach, this hierarchic pluralistic approach, is neither monistic nor instrumentalist about quantum mechanics. So it takes quantum mechanics seriously, but denies that it's exhaustive, that it explains everything in nature. All right, okay, thanks very much.
Hello everyone, I'm sorry I couldn't welcome you earlier, but my name is John Bryce. I'm a fellow here at Ellis College. I'm dressed this way not only because I like it, but also because I was in the governing body meeting with some of the other fellows at this college in at the time that this event began. That being said, I'm now going to give a few instructions about how you can find refreshments. And the instructions are like this. You will go out of that door and then turn right and immediately turn left. And go through a room of books and immediately exit and you'll be in the quad. It's like inverse Narnia, right? And then you go across the quad and I'll be in the lead following you to the common room where there's coffee and you can also enjoy that out in the quad. While you're there, we're going to rearrange the room, turn the lights on, put on a lot of lights, turn on all those on. We do maybe like a few candles. Should we light candles for the
Turn the lights on.
We'll just turn the lights on. But what I'd like to ask you to do, if you can get the beer time with takes time with the speakers, that's great. But if you can't, you can prepare your questions during the break. And that being said,
consistent religions. Yes. At least one rubbish. Right. So my question, if I get to answer questions or how was Aristotle navigating if it took us to mechanics to work out? Is the question I'm going? Yes. You're welcome. You've got a better phrasing. You're welcome to have my question. Feel free to say. Oh, well, that's all right. It's better. Yes, it's well, we're on very, very good. Designing in that case, you've got to see physics.
Well, I don't know. Before that said reserved, and they were like, oh, go and sit at the front. There are 10 free seats at the front. So I guess
I think it's fine.
I think it's probably fine. Yeah.
And it's a circular length. Yeah, that's you got a reading this from the couple of lectures.
Have they sent you anywhere? It's here.
Not in this one. Maybe in another. Yes, but not here.
David, can I just get more mic? A bit more volume, more mic. I wanted to very quickly note that we've arranged a special choral evensong in the Oxford style for middle-sized things like you and me. And that will be at 5:30, ending promptly at 6. It's not close to my mouth. I'm doing what I can. 5:30 to 6, a special choral evensong arranged for middle-sized substances like you and me, followed by a mass for St. Philip and St. James the Less, which is also a sung mass with sermon, which you're welcome to attend. That's in this very space. So we'll end at 5:20 so that it can be converted to its ordinary use, having completed its extraordinary use. That being said, I will turn this over to our discussants with Ellis and Koons, and that is Professor Mark Harris, who is Professor of Science and Religion in this very university.
Thank you very much for the discussion. Actually, it's not hard.
Thank you.
How's that? Is better? Yes. Good. Okay, well, good afternoon, everyone. Great to see you all. I have two fairly straightforward, slightly provocative questions to start with, and then I'd like to open things up to the audience. And we've been told we do need to finish very sharply at 5:20, so I will wrap things up there. So my first question is, Rob and George, I did notice a kind of contrast in approach, really. So if I can construe things like that. Rob, I think you were telling us that Aristotle provides a fairly complete metaphysical system for science and allows us to recover the middle-sized regime, whereas George, I got the impression that you don't need a system. In fact, I think I only heard you say Aristotle's name once, if I heard it correctly. Instead, we need intuitive pictures and diagrams like you're
philosophy of nature is something that's, I think, disjointed even from practicing science. Right? I mean, scientists don't really need to bring in Aristotle's four causes explicitly and model the universe. But I think that my perspective is that philosophy of nature is helpful to us as human beings who are doing science to understand what we're doing, and how it fits into a larger picture in a sort of coherent way. And I think that's pretty much what Joe is doing as well, showing us how we can sort of think of ourselves as purposeful, meaningful agents, right, doing science in a world that is that involves lots of stuff that doesn't seem to be meaningful and purposeful.
What's your perspective, George? Well, I think we're on the same page. I didn't mention Aristotle very much because I will be talking at length about the different kinds of Aristotelian causation tomorrow in the workshop. But I certainly believe all four kinds take place. Now, having said you have to update them, and I will be talking about updating them, you have to update them in two ways, particularly. He didn't really, as far as I understand, I'm not Aristotelian scholar, he didn't really distinguish between time-dependent and time-independent causation. And he kind of had of course, the primary thing is he didn't know about the hierarchical structure. So you have to add those two things to what Aristotle said, and I will be trying to put that together tomorrow. But I certainly...
You have very crude versions of it, right? I mean, the elements and the mixtures of the organisms.
Yeah,
so.
but you had the biological emergence in which I will have tomorrow. You didn't really understand.
Oh, I think he did. He understood that. Because he recognized that organisms are obviously made of elements and mixtures in various ways. That there is some bottom-up constraint. You can't eat aluminum, right kind of elements. But that the soul, it grounds powers like sensation, reasoning, and so on, that can't be explained in a bottom-up way. So I think that's kind of divergence.
Sounds like we'll hear a bit more tomorrow. Anyway, thank you both. So here's a second question. We're in this marvellous theological space. I'm a theologian myself. I'm quite interested to hear about some theological perspectives here. Of course, I know that theologians tend to take the long view, and we never abandoned Aristotle to begin with. And we're quite happy talking about all-sized things having causal properties as well. I don't know what we do if we lost that, actually, but we do. So quite apart from questions about whether God exists or not, do scientists need to learn from theologians about this? And if so, what ways might they learn in today's society? Maybe, George, maybe you can start first.
One must be very, very careful about saying to scientists they can learn from religion. The average scientist will react very, very negatively to that suggestion. Nevertheless, if one is very careful what one says, the scientists try to not refer at all to final causation or briefly mention this, the paradox of how they live their lives, doing their science and saying it's all just particles or forces that they live within their daily lives, and that is the thing. And I think that there is a role to say that there is, I wouldn't go very much further than to say that theologians can say to scientists, surely you have to agree that final causation takes place in the real world. I think this is the kind of thing that they can say without being contradicted.
Yeah, I mean, in fact, people in the hard sciences have made a lot of progress in studying emergent systems, things that are not occurring at the fundamental level. So fortunately, kind of metaphysical philosophy of nature that they all subscribe to officially hasn't actually limited that much in terms of pursuing understanding nature. So I think one thing I can contribute to Aristotle contribute is keep at it. Go ahead. This is right. Don't worry that you can't reduce it all down to the particle physics
possibility spaces. And there are many different kinds of possibility spaces for physics, for biology, and other kinds of things. Including paradoxically, there's a possibility space for thought. This is described by Louis Borges' wonderful novel, The Library of Labour. And the deep question for cosmology is where do those possibility spaces come from, and what are they telling us? I think that's the deep question for cosmology.
Well, thank you both. So I'd like to start throwing questions open to the audience now, and I think it's a roving night, so your hands got up over here, so I think you were momentarily first, actually.
Thank you very much, both of you, for your very, very interesting talks. And I guess I wanted to point out another, maybe more specific contrast I noticed. So, Dr. Ellis, you generally argued that that there is no obvious agency or purpose at the kind of galactic scale or at the microcosmic scale, and you sort of leaned in specifically on the level of proteins where you start to see agency and function.
The level of proteins is the first level.
Whereas Rob seems to suggest that there's a deeper sense, at least of final causality and whatnot. And so maybe to kind of hone in very particularly, is there any sense in which you would talk about a kind of functionality or agency in an inanimate system, Dr. Ellis? So take for instance a star, like first generation star that is producing the first higher level atoms or nuclei, or say, carbon in the center of a mountain that is undergoing change to become diamond. Is there any sense of agency or functionality you see in that at all? Or so between the two of you, how would you talk about any sense of purpose or agency there?
I would resist the suggestion of purpose or agency. I would say there's dynamics taking place where there simply isn't a purpose. And I think, as far as I'm concerned, the star has no purpose, the moon has no purpose. An atom as such has no purpose. I would stick to it.
Yeah, so there's definitely a difference between us on that point. I want to use notions of teleology, final causation purpose more broadly. Now, obviously, I agree. Purpose is defined in biological things. It's a lot more interesting and important than anything you might find in the inorganic world. But I guess my strategy or my thought is that there is a real continuity, nonetheless, between things like extraction principles and equilibrium dynamics and so on, and the kind of purpose that you see in biological organisms around us. And so, if I can get the physicalist and see that, okay, there's a kind of conversation, then maybe it's easier for them to see. Maybe biology is really interesting and powerful notion of purpose. But it's a difference, I'm not sure how deep the difference is. It's certainly
But you see, the context we're in is that even a lot of biologists deny purpose and agency. That's the one I would like to find.
Yeah, I agree there. There's another question, the second question is right here.
Thank you. I've had a lot of discussions with the physicist Sean Carroll about the possibility of fundamental macro-level causation, both seem sympathetic to. And he assures me his view is that this would be very difficult to fit with current physics, and his reasoning is that it would be inconsistent with the principle of locality. Because if a particle behaves differently when it's in a complex living system than outside, he thinks that would be inconsistent with the principle of locality, and this would get us into trouble potentially with special relativity. And so this is all a bit above my pay grade, but I was wondering how you both respond to that argument against causation at middle size level.
So you have to.
So you see causation at the middle size level, why it's called locality. This makes sense.
Locality.
According to Sean Carroll, don't shoot the messenger.
According to Sean
Carroll.
Yeah, Sean Carroll's made this argument against this kind of top-down, middle-sized causation.
I And he denies downward causation. Various fundamental physicists do, because their entire experience of physics is restricted to a small corner of theoretical physics. He doesn't even understand particle physics. He doesn't understand the existence of quasi-particles or he's never ever looked at many branches of physics without causation does take. So I'm not worried, frankly, because I think he comes from an extremely restricted part of physics, and his worldview is restricted by the part of physics that he comes from.
I have to say, I don't know this paper, so I can't really see any problem with calculation. I mean, it strikes me that you must be assuming some very simplistic version of how this would work, but I can't see why a little imagination couldn't make an Aristotelian picture fully valid.
Well, he criticized me by saying top-down causation can't take place seriously. His example was a snowflake, and the fact that snowflakes have got these things which are determined by the context, and he says that's an example people give of top-down causation, and it's not very interesting. It's not the kind of example I would give. The kind of example I would give is the example of the existence of Cooper pairs enabling superconductivity, the existence of phonons enabling all sorts of properties of materials, and then all the top-down causation biology, which I will be talking about tomorrow. And he doesn't talk about any of these kind of top-down causation very actually.
George, you added to my heart to hear some examples used from metaphysics. We had another question, third question over here, I think, and a fourth over there.
Thank you very much for your talks and for your research over the years. I'd love to hear your thoughts on how your views on Aristotelianism, whether that's with the open systems model or with perhaps a more Thomistic approach, a slightly more Thomistic approach with causal powers in substantial form, could shed light on more modern questions such as the Wigner problem. The Wigner problem, the unreasonable effectiveness of mathematics in the physical science. Sorry, my accent is a bit. Or also on fine-tuning. If there might be a way for perhaps the very devout Aristotelian with something like substantial form as the intrinsic and complete constituent principle and causal powers, being able to circumvent a design argument. I'd love to get your thoughts from both of you on those two questions.
So whether Aristotle allows to circumvent the design argument question?
To not require a designer.
Because what? Because the universe itself has certain causal powers that can manifest themselves in this way. Yeah, so one could go, who was it? Tom Nagel has this view, right, where the universe itself has some kind of teleology that drives it towards life. That's possible. And I don't think you have to adopt that view of Aristotelian. You could certainly. A lot of my friends who are Aristotelians sort of forget about lambda 12, right? That Aristotle was a theist. That seems to be, even if you know the creation of time, he did believe in the kind of design of the universe ultimately. So I think that's compatible. The design view is compatible with Aristotle. Look at me about fine-tuning and technology and
I think fine-tuning can be taken as some kind of evidence. It's certainly not conclusive, but my colleague Martin Rees says that fine-tuning is proof that a multiverse exists. And people state that very strongly. And so so it's the contrary of Occam's razor. I think there's a philosophical thing there that it is possible that a multiverse exists, but I don't think we will ever prove it exists. So I place it straightforwardly as a philosophical argument, not a scientific argument, and Mark Marie says it is a scientific argument.
Do you have any thoughts about Baker's unreasonableness?
That is a very, very interesting one, and it goes back to Galileo, actually. And it is very strange that at the fundamental level the universe is described by mathematics, particularly by symmetry groups, SO3, root 5, and that kind of sort of stuff. But, and I think it's just one of the fundamental puzzles. Of course, what is very important is its emergence is based in breaking of symmetries, not in symmetries as such. And that is a very important thing as well.
Platonists find it easier to grapple with this unreasonable effectiveness of maths. Yeah. And you take the causation of abstract objects pretty seriously.
Oh, yes.
Yeah. So I think you've got to get up on that. Right?
Absolutely. Yeah. But that causation takes place through the human brain and through the structure of computers. But nevertheless, given
not out there in nature.
No, but those do exist. We may not, given that they exist, abstract things do have causal powers. There's no question about it.
We have another question here, and there's a lot over there. Thank you for one last Andy, you're next.
Thank you both very much for your talk. I'm a theologian, but I'm going to trade on Professor Ellis' Nevertheless, which came after your statement that you will be loath to advise any scientist to take advice from religious believers. So, Quine is famous for denying that there is any first philosophy, that there's any need for first philosophy. But my intention, humbly, would be that actually, probably science does need first philosophy, and that theologians have historically been in a very good place to provide it, and that there are questions to which theology can still provide the hint of answers for the first philosophy of science. So, for example, we talked about multiverses and the question about whether it's a philosophical issue or whether it's a question of observability. If it's not observability, then it's not science. Why do we think that sense perception is reliable, and why do we think that it's beneficial for humanity in the kinds of way that science shows? There's questions about the nature of induction, which perhaps theologians can, a theological perspective can contribute to. There's a bigger problem which has already been mentioned. And then there's the question of realism. I mean, Einstein was not a Christian by any means, but when he appealed to God's not playing dice, there was a realist principle which was in play. Now, I realise that in quantum mechanics, that's still very much up for grabs, but the realist intuition is something which maybe, again, a Christian first philosophy can contribute to, and dare I say, Thomas Aquinas perhaps even Karl Barth have done so.
I think we can certainly help scientists avoid really bad science. So when Pusey talks about nothingness creating the universe and stuff, and that's really bad science and those bad philosophy. And another example I use a lot is behaviorism. So that was the thing when I was young in psychology. There's no mind at all, no consciousness, there's all behavior. Well, the first philosopher said, no, it's not right. So you would have avoided wasting a lot of time on a project that didn't do that. Philosophy, not science?
Kind of philosophy,
yeah. Or theology.
Or theology.
I'm doubtful of theology.
I doubt that you can do something about it.
Okay. There has to be, as you might say, a kind of presupposition that the world makes sense. That's the sort of question I would take. The human beings were somehow constantly
whole, and like a top-down way. And yet, we think about a planet or a galaxy, talk about the Koons cosmological constant. It seems like there's almost a teleology there of a whole planet or a galaxy acting for the purpose of a part. If we're talking about middle-sized objects, the flourishing of middle-sized objects, the significance of middle-sized objects, the existence of things like frogs and humans and plants. Do you understand the question? The question is about teleology acting for a part as opposed for the whole.
So the question is something like this, I guess: is there any room for a notion of teleology applied to the stars and galaxies? You can definitely say no.
Actually, I think I'd like to come back to that. What I think theology can tell science is not how to do science. It's to tell science something that does not encompass everything that is worth doing. I think that is what theology can tell science. And that is a very important statement.
But science doesn't exhaust knowledge.
Science doesn't exhaust knowledge, yes, correct. And I think that
It seems to obvious to me. Something self-defeating in that sense. I would love to find some teleological factors at the level of the galaxy. I have no idea. That's true.
Isn't that what you were saying, the fine-tuning of the cosmological constant for life?
Fine-tuning, right.
The cosmological constant for life is kind of a teleology of a large-scale system for middle-sized objects.
Right. Well, that's true. You mentioned that. I said that fine-tuning the universe so many galaxies possible. And galaxies are necessary for life, so it's plausible, certainly, to think that that's like a kind of purpose.
So we have time for one, possibly one, two more questions. One here.
Put it very close to me.
I was hoping that you could fill in the details of connecting the examples of emergent laws in chemistry, for example, or in infinite kind of quantum mechanics to formal causation. You went from one to the other, but it was too quick.
Right. Yeah, those are good questions. So if we could discover in these models the kind of structure we need for chemistry and thermodynamics, where the models were finite in nature, so they actually modeled the actual number of molecules or particles in a given system, and just look at the interactions, the pairwise interactions among those particles, then you could treat the whole thing as a heat in Aristotle's sense, and it's kind of form. But the very fact that that kind of model is inadequate, it just doesn't give you the structure that's there to refine chemistry and thermodynamics. That suggests, I think, that there's something else going on here that does impose chemical and thermodynamic structure onto the materials that we're studying. Right? And that's going to have to be something that does something top-down kind of way. So the fact that the matter is organized in molecules with a certain chirality, let's say, or a certain dimensional structure, that's not explained in a bottom-up kind of way with particles combining certain things. It's rather explained by the fact that the whole system has the body of water, let's say, has a kind of watery form, which is responsible for that molecular structure, right? And so, that's the most of the story. You need an irreducible element of the top that moves the parts of the chemical form and the form. Both subjective form and also access.
Feeling the stuff coming through people very much wanting me to pull forward theology out of science. You can't do that, but what you can do is firstly say that science does not encompass all that going on, but you can go to the fine tuning and you can say there are 4 kinds of arguments you can give them. One is that fine tuning just happens. It's not probable, it just happens science, and that's it. That is a philosophical, absolutely solid position that nobody likes because it doesn't go anywhere. The second is you can say that it had to happen, it's the only possible thing that could happen. And the physics project to go to a theory of everything and try to prove there was only one possible theory of everything has failed, it has collapsed in the mass, and that has not worked. The third possibility is to say that it happens because it's to go back to say, why is your multiverse problem? Well, you just showed the thing at one level up, and you have to say, why is your multiverse problem? And any attempt to show it's highly probable involves a series of theories by which you measure and create the possible, and they don't solve it. And the final one is to say, actually, it is evidence of purpose in some kind of sense underlying the universe. And I think that those are all the four options, and I think you can quite strongly say those are the only four options. And if you can prove another option, I'd like to see it, but if those are the only four options, the teleological one for the universe starts to look actually quite good.
Thank you everyone for your questions. I realise there's quite a few more hands up, but we've reached our hard limit of 5:20, so we need to finish now. Please would you show your appreciation for our two speakers.
Staying for even some 5:20 and 5:30, and then probably at 6, so you can get to something else you might be going to. There's currently other services around the start of 6 as well, but there's Mass here. And we'd like to thank UT Boston, the Civitas Center there. We'd like to thank All Souls College, who is hosting us tomorrow, with Professor Bouverie Pusey as our sponsors, as Lifetime Fellow there, and Pusey House. Well, I'm thanking myself, others with us, but Pusey House as as the host of this event, and to the good professors and to discuss. Thank you so much for coming in and doing a wonderful job. And we're going to continue some workshops tomorrow, but we will record them, and eventually the workshops will show up on Pusey House's YouTube site and perhaps further afield, so you will be able to see what happens in the workshops. But we only had room for about 40, and it filled up pretty quickly. So look for that in about a month's time on the Pusey YouTube channel. Thank you.